So welcome to this presentation, and so I will be talking about the possibility for connecting industries with reliable low latency communication. And I want to start with, since it's about going to new use cases, of illustrating a little bit what do we mean with the potential of transforming industries. So let's go back in time, something like 150 years into the 19th century. And this was a time when the key developments were made in utilization of electricity, so electricity generation, electric motors, the light bulb was invented. And at the end of the 19th century, there was a massive build-out of an infrastructure of centralized power stations in order to bring electricity to households. And the motivation was to enable a transition from the gas and oil lighting which existed at that time towards electric lighting, which has a higher quality of experience. It's much brighter light, significantly reduced fire risk, and it is much cleaner. But once there was a build-out of an infrastructure, it had the possibility of having an availability of a resource which has much more potential. So the way on how we live, or our grandparents lived, has changed tremendously by having this availability of electricity. So there was a lot of innovation in other areas, like how we organize our lives with the electric home appliances like refrigerators, stoves, dishwashers, washing machines, heating, ventilation, and how we spend our spare time. And this is on with all the home electronics like radio, TV, audio systems, and so on. So the availability of an infrastructure which provides a good of value has changed other industries as well. When we think of the ICT situation today, we have mobile communication has over the last 30 years revolutionized the way on how we handle personal communications. And we have an infrastructure installed which reaches 90% of the world population. There are 7 billion mobile network subscriptions. And the installed communication infrastructure has over time also significantly evolved in the capabilities that are being provided, from going from some tens of kilobits per second peak data rates all the way to the area of gigabits per second today. And at the same time, the latencies have reduced from several hundreds of milliseconds down to the order of 10 milliseconds. So this availability of an infrastructure is an enabler for making use of this in other segments beyond the personal communications. And maybe in parallel to this communication capabilities, something similar happened in the area of computing. Today, there's on one hand distributed computing, which is going into any kind of object in the physical world, all the way down to a smart toothbrush nowadays. And on the other hand, with cloud computing, there is simple, scalable and cost-effective access to an abundance of computing power in cloud centers, and that means that we have computing on different levels together with communication. This is a game changer for enabling new services. And so it will be different industries which can make use. So the more we go into digitized processes in different industries, the more they can exploit this communication and computing that is available. And that means that the infrastructure which is in place can be exploited in different forms, that different industries are now making use of the computing and communication infrastructure. And this is starting to happen already. Automobiles are being connected via cellular networks. Containers are being connected with and equipped with cellular communication. So we see that the networks will address much broader use cases in the future. And there are a lot of these new cases are in the field that we call machine-type communication, where there are these two variants. On one hand, there's massive machine-type communication, the communication of all these sensors, which are used in a variety of use cases. And here in this presentation, I want to focus on what we call critical machine-type communication, which means it's about providing very low latencies with high reliability for connected industries. So there are different use cases in various fields for this reliable low latency communication. And what it really is about the capability for providing guaranteed in-time delivery within a certain delay bound. And there are the fields where this can be applied is from the area of smart manufacturing, remote control of machinery, either because it's in remote areas or because it's in hazardous environments. It's about intelligent transport systems. It's the distribution automation of the smart grid. It's the use cases which can be, or which are collected under the term tactile internet. It's process automation, it's automated guided vehicles, to name a few of these examples. But when we talk about guaranteed in-time delivery, there's also a different way on how we have to address the requirements. Because when we think on the right-hand side here about how we provide reliability or normal reliability for mobile internet services, the metrics that we typically investigate is kind of what is the average performance that is achievable, which here we show, if I show here the distribution function over latency, which means how can we improve the average, how can we improve the peak, and then there is some kind of measure for the distribution by looking into a 90 percentile or 95 percentile. But when we want to provide guaranteed delays, then all the effort goes actually into the highest part of the distribution, which with the reliability level being a number of nines that we want to focus on. Because in some of these use cases, even if a packet is delivered much faster than what is required, there's not an additional value, because there are often these systems which operated within certain cycles. So it's really the tail of the distribution to focus on. So one of these most demanding use cases that we have discovered is in the area of this factory automation or smart manufacturing. And there it's a controller in the manufacturing cells, which is communicating with different sensors and actuators. And the possibility, and we've heard about this a bit before, on wireless communication is that it provides a lot of flexibility of implementing such a manufacturing cell and configuring such a manufacturing cell, but also that it provides efficient communication to moving parts. The requirements that we can find, if you look a little bit in the literature, is that it's communication with delay latencies in the order of a millisecond end-to-end. The packet sizes are rather modest. It's control messages and simple measurements. And reliability requirements are described to go all the way to 10 to the minus 9. And this is an area which cannot be addressed with very low latency, with high reliability, cannot be addressed with any kind of wireless standard that exists today. And the question is it possible to address this? So from our investigation, we thought if we want to have 1 millisecond end-to-end delay, let's say we have a fraction of this available as a time budget on the radio transmission. So is it possible that we can transmit a packet very reliably within 100 microseconds? And when we look into this, into transmission over a radio channel, then there's inherently a lot of uncertainty in a wireless channel. So by providing high reliability, all the way, let's say, in the order of 10 to the minus 5 or 10 to the minus 9, which corresponds to 10 to the minus 5, which means that we have transmission failures during 5 minutes during 1 year of operation, and 10 to the minus 9 is the equivalent of 30 milliseconds. If we want to provide this kind of reliability levels, which are claimed to be necessary, then there's a lot of margin that is needed in an uncertain wireless transmission, which is in the order of 50 to 90 dB fading margin. And if we introduce now a diversity into such a system to reduce the uncertainty, then this fading margin can be significantly reduced. So it's for when we have a diversity order of 8, the margin reduces to 10 to 18 dBs for these reliability levels. Or if we go to a diversity order of 16, then it goes even below 10 dB. So this is the price that we have to pay together with the diversity in order to address and guarantee this reliability. And the diversity can be provided in the spatial domain, in the frequency domain, but typically due to the delay constraint, not in the time domain. And then, of course, you have to provide the right coding in order to exploit this diversity. From the coding and modulation, I mean, since we're talking about short messages to be transmitted, in that scenario where convolutional codes are very efficient in providing good performance over short messages with effective code rates in the order of half to a third rate. And then in order to be spectrally efficient for devices which have good signal-to-noise ratios, to be bandwidth efficient, higher order modulation is beneficial. So what is the right waveform and structure in order to provide high reliability at low latency? For the availability, we want to have a control of the interference, which means some kind of orthogonal structure is very beneficial for managing the own interference. And if there are external interferences, then some margin is needed to protect against those. But internally, by having an orthogonal system, this is a way on how you can protect against other interferers. At the same time, for the low latency, it's very important to think of very short access slots, because there's an inherent delay from getting a message to when is the next opportunity for you to transmit the message. So a short time slot of 100 microseconds or less is required in order to provide these very low latencies. At the same time, we want to enable very efficient and fast decoding of the data, which means that we want to enable on-the-fly processing at the receiver as the data comes in. And this speaks in favor of having very early channel estimations so that the decoding can start as the data comes in. So that means that the reference symbols should be very early in the data transmission. Again, here, I mean, the advantage of convolutional coding is also that the decoding can happen at an early stage, in contrast to iterative coding, where you first buffer the data and then iteratively decode it. And there are different types of traffic that need to be supported. So there will be periodic traffic and sporadic traffic. So different scheduling regimes are needed to support this, like persistent scheduling for periodic traffic and dynamic scheduling or contention-based transmission modes for sporadic traffic. And all of those need to be sufficiently dimensioned to have the right reliability level. But it's not sufficient only to think of to a single link on how can we get the right reliability and performance onto this, because if we think system-wide, then we also have to protect on that this reliability is available everywhere, at least in the area of interest. And there, it's more than only the fading, the fast fading that needs to be considered. It's also the shadowing of blocking of signals. And so some kind of toolbox of multi-connectivity is needed, where coordinated communication from multiple sides, from multiple points, over multiple frequencies is a key capability in order to provide the diversity and the robustness also in the spatial domain. And then thinking of cellular communications, there's always the option of a fallback to the other radio technologies that are typically provided by the same infrastructure. So having thought about now a little bit the radio communication part, it's also the architecture which must enable this new use cases to be addressed. And we have seen actually this slide before in the first presentation yesterday, so I only pick up some of these things. From the network architecture, the network will evolve in the direction that it will be a distributed cloud infrastructure with central and distributed data centers. And virtualization is the functionality which enables to provide the functionality on this platform. And this can be the network functions themselves, but it can also be the platform for providing application functions for the services directly. With some software-defined networking and configuration, there's an orchestration is needed in order to provide a configuration of the network which is very much adopted to the service we have in place. And for low latency, and I think we have talked about this a few times during the day, this means that a lot of the functionality needs to be provided at the edge, where the transmission delays are simply are bounded from the backhaul and core network perspective. And that means that this is a toolbox also for providing an efficient network slice, which is optimized for the services to be addressed. And with this, I think I'm right on time. I'm at the end of this presentation, where I want to say ICT, with all the development we have seen, is an enabler for enabling industry transformation for industries which are moving into digitized processes. And cellular communication has the role to play of providing ubiquitous connectivity with broad capabilities and an enormous economy of scale and future-proofness by this. So 5G will be a technology which is also addressing and looking beyond the personal communication space of really trying to address the requirements of new use cases. And this includes ultra-reliable, low-latency communication. I think that's very important also that we get into this interaction with these industries which define the requirements and the use cases. And what some of the features which will bring us in this direction is diversity is a key issue for providing the reliability and multi-point communication. It's frame formats which are designed for very short delays, and it's a flexible network architecture which enables us to have a service-optimized network configuration. And from our first studies, we really believe that it will be possible to have ultra-reliable wireless transmissions in the air, in the order of 1 millisecond end-to-end latencies. And with this, I'm at the end of the presentation. Thank you.
So thank you very much, Joachim. I'm sure that we have some questions here. So should we start, Mikivon?
Thank you for a nice presentation. I think it would be quite different to guarantee that low delay, low latency for already established connection and to do the same for random access style communications. So do you think it's really possible to guarantee that low latency for random access based services?
I think the reliability in random access is very much a dimensioning problem, and this depends on, I mean, you have to understand the use case, how many devices try to access the system. I mean, some of the use cases tend to have a traffic profile where a lot of periodic transmission happens, and that you know in advance and can provide the resources in the right times. So for sporadic data, you have to provide the right provisioning of resources at the right timing that enables that collision probabilities are sufficiently low. So that for sure is an issue that you have to make the configuration according to the specific use case.
So I mean, as soon as we have just a few connection attempts, then we need lots of redundancy for reduces for random access to guarantee that low delay. So, and I think the bandwidth requirement or the room for that kind of thing grows exponentially. So, how do you think, or have you done any calculation about that?
We haven't done any specific calculation now. And this is very, as I said, very use case specific, where you have to. Actually, we did for one use case, we did a little bit of simulations, but it's very hard to give a generic reply here because I mean some of these use cases are very localized, and then you have to provide the right dimensioning of your resources for this use case. I think what is important here is the flexibility for having the configuration, the possibility to configure a network slice accordingly. So that I think is a key issue. But then, of course, any kind of providing reliability always comes at the cost of having providing the right resources to address these reliability requirements.
Jens?
I love your comparison with the electricity system, and I think there are lots of parallel, but some of the extrapolations from that could be a little bit interesting. I mean, if you look at electricity started out the same way as telecommunications, started out as a service. Edison installed lights and provided lights as service. And so he owned everything. So both the content and the service was sort of run by the electricity company. And then, but in the electricity world, you have gone to a situation where you have separated the content completely. I mean, the refrigerators and toasters, they are independent of the electricity, and the content, even the content of the energy and the network is now separated on that. What kind of implication does it have to ultra reliability? I mean, can we live in a world like that where you actually there's only connectivity basically that is provided by the network, and so we really have the separation of services and I see some problems there because particular. I mean, you can get to 1 millisecond delay in the radio link, but it's still very much dependent on where you put your computing in the delay loop. Can you comment a little bit on sort of that topic?
I don't think that we can provide the solution here only on the radio or in the radio network. It must be the system architecture which supports this, and here this flexible network infrastructure which allows to have a configuration of, let's say, the end-to-end network for this specific use case is a key feature where you can have functionality located directly at the local place where the execution has to happen. And so some parts can be centralized, some parts need to be distributed because, I mean, here the entire solution needs to be provided, which means there must be the possibility of having the local controller connected locally.
Yeah, exactly. But I think this is a very nice vision, right? And the slices is sort of a secret sauce that would sort of solve all of these things. But I think there is a lot of research going in to make sure that this distributed data center can provide sort of all the functionality and storage and processing with these extreme requirements. So I think there is as much work that we are now discussing the radio part of this. It's of course as much work needed in order to make the complete chain work. And I think we have come a little bit further now. I mean, we have seen the presentations here today that we can see that there are ideas how we could do this air interface in order to be able to address the different properties. Although that's not complete either, but we are starting to see solutions, and we have sort of visions on this side, and I guess that's a little bit another set of conference to dive into the distributed clouds and the performance of these.
And of course, here there are also different options. I mean, the distributed cloud can be used for being the execution platform, for example, for a controller in this, let's say, smart manufacturing use case, or it can be that it simply provides the interconnectivity to a dedicated local controller which is independent from the cloud. I mean, it's a flexible network solution.
Yeah, there are actually two types of offerings here that are mixed. So.
Exactly.
Yeah.
So I think we will close here. So a final thank you, Joachim.